Well, hello there, fellow mathematicians. Today I will be posting my first video when it comes to solving math problems. And what I want to start with today is a beautiful integral that I found on MathStack Exchange. What I'm referring to is the integral going from 0 to infinity of the inverse tangent of the tangent of x squared over x squared dx. The reason why I believe it is very interesting is because, first of all, we have to remind ourselves of a particular case of Lobachevsky's formula. What it says is that the integral going from 0 to infinity of sine of x squared over x squared times f of x dx equals the integral going from 0 to pi over 2 of simply f of x dx. Now, of course, there are some assumptions. First of all, f must be pi periodic. So that means it has a period of pi. So no matter how many times you add pi or you subtract pi, the result is still the same. And it must be even, as in f of negative x equals f of x. Now, if we come back to our initial integral, you might wonder, well, how the fuck can we get it to look in this way? Well, you have to force things out a little bit. Yes, we are able to write it as such. It's just that we can take out a sine squared of x and just put it here in the denominator so that it eventually cancels out. So what you're left with is sine x squared over x squared times the inverse tangent of tangent square x over sine squared x dx. Now, let's see if f of x satisfies these two conditions. Is it pi periodic? Yes. Is it even? Well, yeah. So, by that particular case of Lobachevsky's formula, we have that this integral is the same as the one going from 0 to pi over 2 of the inverse tangent of tangent square x over sine square x dx. And now what I want to do is substitution, because I think that's the most plausible approach as of right now. So we have tangent of x equal to t. Now we do assume that this is an improper integral. It does say pi over 2, but just so that we avoid rigorous notation, we don't say the limit as, for example, t approaches pi over 2 from the left side, but simply put pi over 2. This will already be interpreted as a limit. It's just that so we don't have to write the limit, blah blah blah, for the 10,000th time, for example. So we're gonna go in this way. Tangent of x equals t, which, after a bit of calculations, you notice that dx is actually going to be the same as dt over 1 plus t squared. Since we were initially integrating from 0 to pi over 2, now we're going to go from 0 to positive infinity. The reason it's positive infinity is because we're checking a lateral limit, not the entire limit as a whole, because the limit as t approaches pi over 2 of tangent of t doesn't exist, but its lateral limits do, and that's what we need to use here. If we were to take pi over 2 from the left side, well, then this will just jump all the way to positive infinity. So that's what we did here. So now what we're left with is the inverse tangent of t squared. Now sine squared of x is just the same as 1 minus cosine squared x, but mind you, cosine squared x is the same as 1 over secant squared x, which overall is just going to be 1 over t squared plus 1. And also don't forget about the 1 plus t squared that we got from dx. Just like that. So now this is the same as the integral going from 0 to infinity of the inverse tangent of t squared over 1 plus t squared minus 1 dt. I am so sorry, this is supposed to be a t, not an x. So it's supposed to be dt, not dx. I'm sorry about that. What you're left with is basically the integral going from 0 to infinity of the inverse tangent of t squared over t squared dt. If you compare this integral to this one from before, the only thing that differs here is the argument of the inverse tangent. We went completely from tangent square to t square, which I believe just dramatically simplifies the process. Now, realistically, the only good approach we have here is to go full-on Feynman technique. Feynman technique says that if we define a function I of a, such that it is, let's say, the integral going from 0 to infinity, I will define it as the inverse tangent of a times t squared over t squared dt. I'll also put in the condition that a must be greater or equal to 0. Well, this implies that its derivative with respect to a is the same as the integral going from 0 to infinity of the partial derivative of whatever function is inside, with respect to a, mind you. So we're basically going to have this expression. Oh, and also, this will be valid for any a that is greater than 0. Just wanted to put that on the record. So we're just going to differentiate this function with respect to a. Well, you can treat t as a constant in this case. Technically it isn't a constant, but to simplify the explanation, treat it as it is. So you get the integral going from 0 to infinity of, okay, 1 over t squared is a constant. Well, at least in our case, in our primitive explanation, let's say. So 1 over t squared just goes away. Multiplied by 1 over 1 plus a squared times t to the 4th power. But then you must also multiply by t squared because that's the chain rule, dt. This t squared cancels out, which is pretty awesome. So what you're left with is the integral going from 0 to infinity of dt over 1 plus a squared times t to the 4th power. Which, it looks somewhat intimidating, but this can be approached very easily. Let's take out a factor of t squared from the denominator. So we're going to have dt over t squared times 1 over t squared plus a squared t squared. And now what we should do right now is substitute 1 over t to equal v, which in turn will make dt equal to negative dv over v squared, which in our case will give us the integral from, here it would be positive infinity, and here it would be 0, but we can move this negative sign towards the integral to switch its bounds. So it's still gonna be 0 to infinity. We just don't add this negative sign later on. We don't do that. And what we should get eventually is just dv over v squared plus a squared over v squared, which is nice. And also, since this function is even, well, this is actually the same as 1/2 of the integral going from negative infinity to positive infinity of dv over, this can actually be written as v minus a over v squared plus 2a. If you don't believe me, you can verify this yourself. And this is where Glasser's master theorem comes into place. Okay, well, rather, this is a particular case of it. But when you have an integral like this, with a function that takes the argument v minus a over v, where a is greater than 0, this actually is the same as saying the integral going from negative infinity to infinity of dv over v squared plus 2a. There are some additional conditions you must follow through. I'm not going to specify what those are because I think that is not necessary for our use case here. So we get 1/2 the integral going from negative infinity to infinity of whatever I've stated after that. And now we can turn back to the integral going from 0 to infinity of dv over v squared plus 2a. And eventually, given if you find out what the antiderivative of this function is, you should get 1 over square root of 2a times the inverse tangent of v over square root of 2a. And you evaluate these from 0 to infinity, which in turn gives us pi over 2 times square root of 2a. Just like that. But keep in mind, this is I prime of a. We have to go back to I of a and see what this equals. Well, I of a is just the integral, well, the indefinite integral of pi over 2 times square root of 2a dA. I'm going to take pi over square root of 2 outside the integral, so that we're left with dA over 2 square root of a. And that is exactly the derivative of square root of a. So you can simply write this as pi over square root of 2 multiplied by square root of a plus c. What is c equal to? Well, let's check. If we were to plug in 0 instead of a, what you would get is undoubtedly 0 over t squared, which is 0. As if you're evaluating from 0 to infinity 0 dt, well, that's just 0. So basically, I of 0 equals 0, which implies, which I guess implies that 0 plus c equals 0, which is the same as saying c equals 0. So now we know that I of a, which is the same as the integral going from 0 to infinity of the inverse tangent of a times t squared over t squared dt equals pi over square root of 2 times square root of a. Our main goal was to look for I of 1, since in this case we can just consider a equals 1. So what we can conclude is that the integral going from 0 to infinity of the inverse tangent of t squared over t squared dt is the same as the initial integral we've had beforehand, the inverse tangent of tangent square of x over x squared dx, and that is just equal to pi over square root of 2. This is the final answer. And that's it. That's the solution to this problem. This is how I approached it personally. Your methods might be different, but I'm very interested in seeing how you could approach this yourselves, because there could be many methods, but today I just showed you the one that I came up with. So yeah, that's it. See ya.